Okay, so here we have a sample volume problem. Pause the video if you need to read this. Oh, no, I should probably leave this just so I have that. So we have, oops, can't see that color. We have y equals e to the x, y equals e, x-axis, y-axis, and then now I don't need any. Well, I also need that it's revolved around x-axis. So really this is going to be like an extension of what we did yesterday, where we did area between two curves. Now we've got like volume between two curves. Okay, and really all I need to draw is this axis, or the x and y, because I've bounded it with the x and y axis, so I'm not going to get anything down here. I suppose I could. Yeah, I suppose I could, but I won't. So this is the information that we need. Here's what y equals e to the x is going to look like. That's just an exponential function, which would have its tail coming down at its asymptote. And then we have y equals e, this line here. And remember that e is approximately equal to 2.7185, something like that. So then, when finding the volume, that's going to be this region here. It's going to be this region here, revolved around the x-axis. So what I want to be doing is I want to be setting up my two radius integrals. Remember for a simple volume, it's just from a to b of pi r squared times d, and then whatever the axis of rotation is. So if the rotational axis is x, then we have a dx. If the rotational axis is y, then we have a dy. Now in this case, and I don't know if y'all understood that from last time, but it's almost like I've got two separate integrals that I'm going from a to b. I haven't figured out what a to b are yet. It's from here to here. It's a and b. I just don't know what they are yet. It's almost like we have, hold on, I don't need that. It's almost like we have an integral or a volume of the line y equals e from a to b, and we're getting just a solid cylinder. And then we're subtracting off the volume integral from the exponential function, which is going to be this volcano looking one. So it's like we're finding this volume and then subtracting away this volume. So it's really like I want to get two separate integrals. One that's the integral from a to b for this function. So we have one that's here and then a second one where the radiuses are going to be different, and then we're just going to subtract them in the end. So if we're looking at this one, y'all realize that this e to the x line, or this integral that we would do for this shape, this perfect cylinder, would be larger than the volume that we'd get for this shape. So if we subtracted them in the opposite order, we would get a negative value, because this number is going to be bigger than this number. So that's why we want to do this one first, because it's going to give us the larger number, so that we can get a positive answer in the end. So what would the radius be for each of these circles? Okay, so we'll get that the radius here is e. So, and I still haven't figured out a and b. I'll figure out that in a little bit. So I'm just going to put e squared here dx. Now for this second function, we have to realize what the radius is going to be here. So like I was saying, for this function, the radius is going to be exactly equal to whatever the y values are. But we should notice that the y values are changing. The y values are not the same at any instance. So what we have to do is we have to say the integral from a to b of pi, I like to say y squared dx, but then we've got a y and we've got a dx and we can't integrate that yet. That might be a multivariable calculus skill, but we don't know how to deal with that yet. So what we need to do is we need to turn the y values into x values. And we can do that with the function that it's given us. So we know that the y, or the height of the function, is exactly equal to e to the x. So then my height, or the radius in this case, is going to be exactly equal to e to the x. So we have the integral from a to b of pi e squared, e to the x squared dx. Now I have this in terms of where everything's an x, and I can integrate it from there. Okay, so now we need to figure out what my a and my b are. Okay, so to find the a and the b, a is really easy. We've got the y-axis here. That's one of our boundaries, so that means that a is going to be 0. B, however, is a little bit more difficult. What we're going to have to do is find this intersection point. So to find the intersection point, all we really have to do is set these two equations equal to each other. So we've got the line y equals x squared and the line y equals e. So those are the ones we're setting equal to each other. So I'm going to come back down here and say y equals e to the x and y equals e. So I'm just setting these two equal to each other. So e equals e to the x. So what does e have to be? What power's here? 1. So this x has to also be 1. Thank you, Stacy. So now I have my a and my b. And I'm putting a subtraction sign in between these two integrals. And now we can do the integrals. This integral, while it might look kind of complicated, it's super easy. We've got a number times another number. So all of this is really just a coefficient. So we can just pull that out in front, because it has no variables in it. So the only thing we have is the integral of dx. Minus, and we can also pull this pi out in front. But now we have e to the, do you know what to do with the power to a power? You multiply the two powers. So that's e to the 2x times dx. There is one simplification step that I can do. Oh wait, no I can't. Well, I suppose I could, but it doesn't. No. So this integral is fairly easy to do. That's just going to be pi e squared x evaluated from 0 to 1. However, this integral, we're going to have to do a u substitution. So my u substitution is going to be 2x. My du is going to be 2 dx. So I have to have 1/2 du is equal to dx. So now I can replace that here. So I get pi integral 0 to 1 of 1/2 e to the u du. And actually, really, I should change these values here because they started out, these are the corresponding x values, but they're not the corresponding u values. Now, remember, you can avoid that by, after doing the integral, just changing u back into x. Or, some of you might like it better to change these values into u values right now. So if I plug 0 in for x, I get 0 for u, so that one doesn't change. But if I plug in 1 for x, then I get that u is 2, so I can change this to a 2. Okay, so now I'm going to do this integration here. So I haven't evaluated this yet. So minus pi, and then the integral of e to the u is just e to the u. It stays the same. So we have 1/2 e to the u evaluated from 0 to 2. And now, since I changed these endpoints to u values when I converted them here, now I don't have to change my u back into 2x. I can just go ahead and substitute the 2 and the 0 in without going back to the substitution. So now I can just go ahead and pi e squared times 1 minus 0 minus pi halves e to the 2 minus e to the 0. So all in all, I get pi e squared minus pi squared times e squared minus 1. And I don't... Actually, there are some substitutions that well, maybe not. Well, that's where I'm going to leave this video, because I wouldn't simplify this much further. Okay, so we've got a new problem. It's basically the same problem with all the same information, only this time we're revolving around the y-axis. So we should get the same picture, or the same initial picture. And we want this region. Only this time we're revolving around the y-axis, so we're going to have horizontal circles. Okay, so this time, when we're doing our integral, let me get back to black. When we're doing our integral from a to b, we're going to have dy's this time because we're going around the y-axis. So if we're looking at the if we're looking around the y-axis, and we're thinking about our radius here. So this is what I've drawn here is the radius. So when we're constructing the radiuses here, we're reading that value from the x value. So our radiuses are going to be whatever x is. So here's our radius. So when we substitute in the radius from a to b, we have pi x squared dy. And just like in the last time, I have an x and a dy, so I can't integrate that just yet. So I need to turn this into y's. Now, you should notice something incredibly different than what we did last time. In this one, I'm not subtracting off anything. Can y'all see why I'm... Hold on. So I only need one integral here because I'm not actually subtracting off anything like I did in the previous example. So now our only task is to get this y value in terms of x. So if you remember your log properties, you can very easily turn this into natural log, well, I don't need the natural log of, hold on, no, natural log of y equals x. If you don't remember that, then you can say, you can take this function, and I'm going to take the logarithm of both sides, so I get natural log of y equals natural log of e to the x. So then the natural log of e to the x just reduces to x. And then we end up with this again. So now wherever we see an x, we can put the natural log of y. So the radiuses are natural logs of y. So we get the integral a to b of pi natural log y squared dy. Okay, so at this point, the only thing we have left to do is find out what a and b are. So we go back up to here, and the thing that we want to pay attention to now is that we're doing dy. So when we're doing dy, we should be looking at where our y starts and ends, as opposed to our x starts and x ends when we're looking at dx. So we're looking for this point and this point for our y-axis. So our y-axis right here, we already have this point labeled. It's 0, 1, so where we start in the y is at 1, and where we end at in y is this e value. So those are our a and our b. So we can come back down here and we say a is 1 and b is e. And at this point, this integral is not something that we can really do. We would need integration by parts to do this, which is a BC calculus topic. So at this point, we could just do this one in our calculators. So that I will leave the calculation to you. And so after doing this in my calculator, I get approximately 2.257 if I round.